Hello everyone! This video is entitled Quantum Theory. In this video, I'll explain the formation of atomic sublevels, how scientists arrived at their discovery, and why the existence of these sublevels have caused scientists to abandon the Borh-Rutherford model for an atomic model that is far superior in its ability to explain the interactions of atoms. I also make clear how to describe these orbital sublevels through the use of quantum numbers. If you have not yet watched my video on Bohr's atomic model, it is recommended that you do so first to fully understand this material. You can find a link to that video in the description below. Okay, let's get started. As I stated in the previous lecture, Bohr's atomic model was a pioneering attempt to describe the structure of atoms, but it had some limitations. There are two significant flaws in his model. The first and most sizable flaw was Bohr's inability to explain why electrons could circle the nucleus without losing energy and falling into the center of the atom due to attractive forces. He proposed that an electron orbits an atom in a constant energy state. He called it the stationary state, but he couldn't explain how this was possible. The lack of understanding about electron orbits led to his second flaw, an inability to comprehend the movement of electrons. This limited his ability to make sense of the complex spectral data from multi-electron atoms, those clustered spectral bands you see here. To address these limitations, scientists proposed the concept of energy sublevels to explain the behavior of multi-electron atoms and the formation of their spectral lines. But it wasn't until 1923, when French physicist Louis de Broglie suggested a new way of looking at electrons, that scientists began to understand how these energy sublevels were formed. De Broglie's breakthrough was to use Einstein's theory that light can act as both a particle and a wave to suggest that electrons could also have a dual nature. This idea, later supported by experiments and calculations, was confirmed. Electrons move in wave patterns, not circular paths. Specifically, electrons exist in standing waves, meaning they encounter their own path as they orbit the nucleus of an atom. As you can see in this picture to the bottom left, if the wave path of an electron is not in phase with itself, meaning it's not connected, then the electron will lose its orbit and be expelled from the atom. This next picture illustrates why the location of a particular electron wave path at a specific energy level cannot be exactly defined. An electron can follow many similar paths around the nucleus at a specific energy level. To account for this, scientists assign each electron with a wave pattern that statistically describes its likelihood of being found in a particular energy level. This final picture illustrates that as orbital space increases with each subsequent energy level, so does the number of viable electron paths around the nucleus. Despite this level of uncertainty surrounding the properties of electrons circling the nucleus, including their precise wave boundaries and their exact position within the atom, de Broglie's discovery laid the foundation for scientists to establish a modernized model of the atom. It was because of de Broglie's discovery that in 1926, Erwin Schrödinger was equipped to propose a new atomic model of the atom, our current working model, the quantum mechanical model of the atom. And in the process, Schrödinger redefined the study of quantum mechanics as a branch of physics that uses mathematical equations to describe the wave properties of submicroscopic particles such as electrons, atoms, and molecules.
The uncertainty principle. Immediately after Erwin Schrödinger proposed his new quantum mechanical model of the atom, a man named Werner Heisenberg began to poke holes through it. In 1927, Heisenberg presented the world with his uncertainty principle. Using mathematics, Heisenberg showed that it is impossible to know both the position and momentum of any object. Heisenberg stated that Schrödinger's proposed model could not be possible because it provided a clear defined path for an electron moving at a known speed. Based on the uncertainty principle, if you know the electron's precise position and path around the nucleus, you cannot know the speed at which the electron is moving, and vice versa. Let me try to explain this to you with the use of an analogy. Here you have a moving train. While the train's in motion, you can easily determine exactly how fast it's traveling. However, if I wanted to know the exact GPS coordinates of a particular passenger on the train, I would need to stop the train so I can pinpoint that person's location. It is impossible to know the exact location of the individual while the train is in motion because the passenger would be in several locations simultaneously at the moment you choose to measure his or her position. And so, it gets to the heart of the uncertainty principle. Just like a passenger on a moving train, it is impossible to know where an electron is around an atom if you know exactly how fast it's moving. And so, based on the uncertainty principle, the current atomic models were flawed because you cannot assign fixed paths to the motion of electrons. Schrödinger, photographed here in the bottom right, conceded that Heisenberg was correct. Knowing the exact location of an electron is impossible. However, he thought it might be possible to determine the probability of an electron's location through the use of statistics. Unfazed by Heisenberg's critiques, Schrödinger developed a wave equation to determine the probability of finding an atom's electron at a particular point within the atom. Now, it goes without saying that you do not need to know this wave function. If you want to understand it, I strongly encourage that you pursue a degree in quantum mechanics. It is not the focus of this course. Now, what's great about this wave equation is that it has many solutions. Each solution represents a particular wave function, and each wave function gives information about the electron's energy and its probable location within the atom. Chemists call these wave functions orbitals. Schrödinger was able to take the mathematical idea of a wave function and provide physical meaning to it by squaring that function. The square of each wave function can be used to plot what are called three-dimensional probability distribution graphs. These graphs indicate regions around the nucleus with the greatest probability of finding an electron. These pictures at the bottom of the slide are probability distribution graphs. They're showing the wave functions plotted as orbitals where you're most likely to find an electron. Unlike Bohr's model, where the electron is following a set path, in the quantum mechanical model, we don't know where the electron is exactly, but we can identify these regions of space where we're most likely to find the electron or the highest probability of finding that electron. These bubbled graphs represent the areas where you'll find electrons within the energy levels. Bear in mind, what you're looking at right now are the long-awaited atomic sublevels I alluded to in the last lecture. Each one of these graphs represents a different shape of an atomic sublevel. In the coming slides, I'll explain to you how to make sense of these sublevels with the use of numbers. We call them quantum numbers. These numbers help us organize and catalog all of the different kinds of orbital sublevels. Quantum numbers. So we know that orbitals have a variety of different shapes, but how do we describe them? Well, the answer to that question is through the use of quantum numbers. These are just numbers that are used to represent certain characteristics of each orbital sublevel. Scientists use 4 different quantum numbers to describe an atomic orbital. So the first quantum number, symbolized by lowercase n, describes where the orbital is in the atom, the energy level that it could be found in. The second quantum number, lowercase l, describes the orbital shape. So which particular shape are we identifying here? And as we know, there are different shapes, so which one have we picked out? The third quantum number is m lowercase l, and that describes the orbital's orientation in space. So is it on the x-axis, the y-axis, the z-axis? Which way is the orbital pointing? And the fourth quantum number, m subscript s, describes the orbital's electron spin. So in which direction is the electron spinning within that orbital? Now I know we haven't talked about electron spin yet, but it will be in the coming slides. All right, let's break down each one of these quantum numbers individually. The first quantum number is actually quite basic. It's called the principal quantum number. Again, it's symbolized by lowercase n, and it's always a positive whole number. What it specifies is the energy level of the atomic orbital and its relative size. The higher the number, the greater the energy level, which would mean that you have a larger electron wave or orbital size. So essentially what this is telling us is where we're likely to find the orbital that we're describing. And so if you look at the bottom right, you can see the Borh-Rutherford model that was described. And basically what the principal quantum number is the old school n equals 1, n equals 2, n equals 3. It's basically just the energy level, that sphere that we're talking about, where we're most likely to find the orbital sublevel or the atomic orbital that we're describing. If you look at the bottom image, that bottom image is just an energy diagram. And so that's just telling us how we can, of course, jump between energy levels with electrons. And so the reason why I'm saying there's a higher number, there's a higher energy level, is because, of course, if you go further away from the nucleus, you're increasing in energy. And so that's why you're increasing in the relative size of the atomic orbital. Now, remember, the greatest number of electrons that are possible in any energy level is calculated by 2n squared. And so, again, if I have energy level 1 or shell 1, it's going to be 1 squared times 2, which gives me 2 electrons, or shell 2, 2 squared is 4 times 2 is 8 electrons. So that's essentially how we calculate how many electrons are going to be in that energy level, and then we go from there to determine where those electrons are going to be in which atomic orbital. The second quantum number is called the orbital-shape quantum number. It's symbolized by lowercase l, and it's an integer that refers to the orbital shape of the sublevels within each principal energy level that we described in the last slide. The value of n places precise limits on the value of L, and the value of L can range from 0 to a maximum value of n minus 1. So what does that mean? If I'm looking at energy level 1, I can only have one kind of orbital shape. The reason being is because n minus 1, 1 minus 1 is going to give me 0, and that's the only value I can have. So L is equal to 0, and that's the only type of orbital shape I'm given. In the second energy level, I can have two potential orbital shapes. I can have 0 or 1, because the limit provides 2. If I'm looking at the third energy level, I can have 3 types of orbital shapes, 0, 1, and 2. The best way for me to describe this to you is by the use of a neighborhood analogy. You have to think about it like I have a specific area, and in that specific area, I can only build one kind of house. But if I have a larger area that encompasses the first one, I can build 2 kinds of houses. I can build the house that was built in the first area and a different kind of house in the second area. If I have now a third area that encompasses both the first and the second, I can now build 3 types of houses. The first type, the second type, and now a third type of house. Think of it like I have Scarborough, and Scarborough only builds one kind of house. And Scarborough is in Toronto, and Toronto can build a second kind of house. So now not only do I have the type of house that's built in Scarborough, but I now have the type of house that's built in Toronto. And then you look at the GTA. So the GTA would be the third energy level. And now in the GTA, I can build a third kind of house. So now I have the type of house that's in Scarborough, the type of house that's in Toronto, and the type of house that's in the entirety of the GTA. So each energy level is giving you basically the sublevels within that energy level. And the sublevels can be described by an orbital shape, a specific shape that can hold electrons. And so if I have the fourth energy level, I would have 4 distinct shapes within which I can put electrons. So please note that the number of possible values for L for any given energy level is always the same as the number for N. So if I have energy level 5, I could potentially have 5 different kinds of orbital shapes. That's why energy level 2 has 2 types of L's, 0 and 1. Energy level 3 has 3 types of L's, 0, 1, and 2. So like I said before, for any given value of L, you have a specific type of orbital shape. And so each orbital shape is not only represented by a number, but it's also represented by a letter. So for the orbital shape that's described by L equals 0, we also have the letter S. L equals 1 has the letter P. L equals 2 has the letter D. L equals 3 has the letter F. These letters are actually the start of the name of that orbital. And so the orbital that's described by L equals 0 and S is called sharp. That's the name of that orbital shape. L equals 1 has a principal name. L equals 2 is called diffuse. L equals 3 is called fundamental. And each one of these types of shapes corresponds to a specific location on the periodic table. Now, that point, we're going to delve into that a little bit more, not just at the end of this package, but in the next package. But what's important is to understand what is meant by S, P, D, and F. So if I'm looking at the third energy level, and I want to describe one particular type of orbital in that energy level, specifically, I'm going to describe L equals 0. Well, I can actually use a notation for that description as 3s. And so for n equals 3 and sublevel 0, I have 3s. So that narrows down what I'm describing. I'm describing the sharp orbital shape in the third energy level. I'm describing that particular type of house in that very large neighborhood. In the second energy level, if I wanted to describe, say, L equals 1, I would note it as 2p. And so what I'm describing now, what I'm narrowing down to the reader, is I'm describing the principal shape orbital in the second energy level. I'm describing that specific one. Now, again, bear in mind, for the third energy level, I can actually have more than one type of shape. I can have 3s, I can have 3p, and I can have 3d. And again, the reason why is because the third energy level provides 3 different kind of L's for me, 3 different kind of orbital shapes. I can have in that neighborhood 3 different style houses. Okay? And so what we're doing now is we're just noting how it's possible to identify a specific orbital shape that we're describing. The third quantum number, called the magnetic quantum number, is symbolized by a lowercase m subscript L. It's an integer with values ranging from negative L to positive L, including 0. This quantum number indicates the orientation of an orbital in space around the nucleus. Just like the value of L was limited by the principal quantum number n, the values of ml are limited by the value of L. So, if I have L equals 0, ml can only be 0, because negative 0 and positive 0 is 0. So that's why for, say, energy level 1, n equals 1, I only have one possible type of orbital, L equals 0, which is an S type. In fact, the reason for that is because of ml. Now, if that doesn't make sense, it will when we go over the next point. If you look at L equals 1, ml has 3 possible values. It can be negative 1, 0, and positive 1. What that actually means is for L equals 1, which is essentially a p type of orbital, I can have 3 possible different orientations. So let's take a look. At the bottom there in pink, you can see the 3 different orientations of the p orbital. That p orbital looks kind of like a dumbbell, and it can be facing in the x-axis, the y-axis, or the z-axis. Now, in fact, what this is saying is I actually have 3 different types of p orbitals. So in energy levels that have p orbitals, I always have 3 possible p orbitals. It doesn't mean that each one of those orbitals is going to have an electron. No, it means that the electron can occupy any one of those 3 orbital directions. And so that's why for, say, an energy level that has an L equals 1, I can have an ML equals -1, 0, and +1. In fact, if you look at that little picture with the magnetic field showing there, the 3 clustered bands again. Now it's making sense. Those 3 clustered bands, we've seen them before in the spectral diagrams. Those 3 clustered bands are representative of these p orbitals in 3 different orientations. And that's why you had those photons hitting those clustered lines on that detector, because photons were being emitted by electrons in each one of these 3 p orbitals. Notice that for any given value of L, there are 2 L plus 1 values of ML. Okay, so if I have an L value of 1, 1 times 2 is 2, plus 1 is 3, which means I have 3 possible MLs. The total number of orbitals for any energy level, n, is given by n squared. So this is a good way of really trying to keep a firm grasp on how many orbitals we're describing in each energy level. So if I have energy level 2, energy level 2 is 2 squared, so that's going to give me 4. I have 4 possible orbitals, and that makes sense because in energy level 2, I can have L equals 0 or L equals 1. And so L equals 0 is going to give me an s orbital, and L equals 1 is going to give me 3 different p orbitals. Hence why we have 4 potential types of orbitals. Now, at this point, some of you may be getting confused. You may not be able to see how these numbers all come together. Rest assured that the example I complete at the end of this package will clarify all of those issues you may be having. This concept organizer shows the relationship between the first 3 quantum numbers. For energy level 1, you can have one specific type of orbital shape, the S shape, represented by L equals 0. And that S shape only has one orientation, i.e. it only has one orbital, the ML equals 0. So for energy level 1, you can only have one orbital. But for energy level 2, you have 2 types of orbital shapes, S and P. For the S type, again, you only have one orbital. But for the P type, you have 3 orbitals, -1, 0, and +1. What that means is, for the orbital space that we call energy level 2, that sphere, you can have 2 types of orbitals, but totaling 4 orbitals. So 1s and 3p. And this concept continues for every subsequent energy level. So for energy level 3, you can have 3 types of orbitals, s, p, and d. And for each one of those types, you have the corresponding number of orbitals that you can create. So for the S type, you have 1. For the P type, you have 3. And for the D type, you have 5. Remember, ML spans from -L to +L. And so because L is equal to 2 here, you can have 5 specific d orbitals. This image shows the 4 main orbital types: S for sharp, P for principal, D for diffuse, and F for fundamental. It also shows all the orientations for each orbital type. So for L equals 0, you'll have 1 orbital orientation for S. For L equals 1, you'll have 3 orbital orientations for P. For L equals 2, you'll have 5 orbital orientations for D. And for L equals 3, you'll have 7 orbital orientations for F. Again, this is noted by the ML that ranges from negative L to positive L. So for L equals 0, you have an ML equal to 0, meaning you only have one orbital orientation. For L equals to 1, you have an ML ranging from negative 1 to positive 1, giving us 3 possible orbital orientations. For L equals to 2, you have an ML ranging from negative 2 to positive 2, giving us 5 orbital orientations. And for L equals to 3, you have an ML ranging from negative 3 to positive 3, giving us 7 orbital orientations. The fourth quantum number is called the spin quantum number. It's symbolized by a lowercase m subscript s. This quantum number specifies the direction in which the electron in an orbital is spinning. There are only two possible values for this quantum number, positive 1/2 and negative 1/2. Experimental evidence has shown that electrons spin about their axis as they travel through their orbitals around an atom. This is analogous to how planets spin as they orbit around the sun. Like a tiny top, an electron can spin in one of two directions, each direction generating a magnetic field. Remember that the movement of a charged particle creates a magnetic field. This image to the bottom left shows two electrons with opposite spin and magnetic fields pointing in different directions. When these magnetic fields interact, they create a stable arrangement. It's due to this phenomenon that a single orbital can be occupied by two electrons with opposite spin. In 1925, it was physicist Wolfgang Pauli who first proposed that any two electrons of opposite spin could occupy an orbital. This proposal became known as the Pauli exclusion principle. It's called an exclusion principle because it places a limit on the total number of electrons that can occupy any orbital. This exclusion principle outlined three possible scenarios. The first scenario stated that any orbital can have a maximum of two electrons as long as both electrons are spinning in opposite directions to one another. The second scenario stated that you can have an orbital with one electron of either spin. And the third scenario was that you could have an orbital that had no electrons. If electrons are paired, they must move in opposite direction, one going clockwise and the other counterclockwise, or one turning up while the other spins down. This would create a stable arrangement. Now, if you have an orbital with one unpaired electron of either spin, it is that magnetic field, along with many other things, that allows for that electron to interact with other atoms in chemical bonding. Each electron in an atom has its own unique set of 4 quantum numbers. Let's compare the electrons in a hydrogen atom to the electrons in a helium atom. Remember, a hydrogen atom only has 1 electron, but a helium atom has 2. So if you look at hydrogen, hydrogen exists, of course, in energy level 1. It only has one orbital, L equals 0, an s orbital. And the orientation for that orbital is always ML equals 0. I only have one electron, and so I'm going to note that one electron as MS equals positive 1/2. But if we look at helium, helium has 2 electrons. Again, helium is also an energy level 1, so N equals 1. It also only has one orbital, L equals 0, an s orbital. And the orientation again is ML equals 0. For the first electron, I'm going to note it as MS equals positive 1/2. The second electron will have the exact same set of quantum numbers. However, its MS is going to be equal to negative 1/2. So you can see it's also an energy level 1. It's also going to be in the s orbital because that s orbital can hold a potential of 2 electrons. And the orientation again is of course going to be 0. But the reason it can hold 2 electrons is because the first one is positive spin and the next one is negative spin. Now, I know what you're thinking. You're thinking, why did I start with positive instead of negative? In fact, you can actually start with either positive or negative. They obviously need to be opposite in sign when you're finished writing out the quantum numbers, but by convention, chemists usually use positive when they're starting out a series. So I would recommend you do that just so that we have some continuity. Here we're going to examine the lithium atom's 3 electrons, each of which has its own unique set of quantum numbers. Lithium exists in energy level 2, but before we can put electrons in the second energy level, we need to remember that a first energy level with an s orbital exists closer to the nucleus, and so that energy level with that orbital must be filled first before we can move on to the second energy level. And so, to start off our quantum number series, we need to write n equals 1. And because there's an s orbital, we're going to write L equals 0. Its orientation is going to be ML equals 0, as always. And we're going to fill it with an ms equals positive 1/2 and an electron with a negative spin, negative 1/2. Once the s orbital in the first energy level has been filled, we can now move on to the second energy level, which has its own s orbital. And so we write n equals 2, and for the s orbital in the second energy level, we're going to put L equals 0. Remember that n equals 2 has 2 possible orbitals. It has L equals 0, which is an s orbital, and L equals 1, which is p orbitals. Now, the p orbitals are higher in energy. That's why they have a higher number notation. So L equals 0 needs to be filled before you have L equal 1 get an electron. And so, of course, the orientation for L equals 0 is going to be ML equals 0. And you're going to half fill this orbital with an electron with positive spin. Ms equals positive 1/2. The reason this orbital is going to be half filled is because lithium only has 3 electrons. And we've used 2 of those electrons to fill the s orbital in the first energy level. And so we're only left with 1 electron to put in the second energy level in that s orbital. So to review, the first 2 electrons occupy the 1s orbital and have the same set of quantum numbers as helium's 2 electrons. And that makes sense. So helium looks exactly like the first 2 lines of lithium. The reason why lithium is different is because we now have 1 extra electron in the second energy level. Based on the Pauli exclusion principle, the 1s orbital, n equals 1, is now full. And because it contains the maximum number of electrons of 2, lithium's third electron now needs to have an n value greater than 1, i.e. n equals 2. The n equals 2 value for lithium has 2 potential L values, 0 or 1, 0 being an s orbital and 1 being the p orbitals. Remember that an atom's ground state represents the lowest energy state. Therefore, the lowest energy sublevel, L equals 0, must be filled before you can move on to L equals 1. An atom's chemical properties are mainly associated with its ground state electron configuration. So like I alluded to in the last couple of slides, you have to remember that the reason why we have atoms reacting is because of these orientations and these orbitals and these electrons that are half filled. So if you look at energy level 2, the reason why lithium wants to lose 1 electron is because it only has 1 electron in the second energy level. And that 1 electron is unpaired, meaning the magnetism is not canceled out. And that magnetism contributes to the reactivity of lithium. Hund's rule. German physicist Friedrich Hund proposed a new rule for the allocation of electrons to orbitals of the same energy sublevel. His rule stated that if you're going to add an electron to an orbital of the same energy sublevel, each orbital must receive one electron before any pairing can occur. So if you look at carbon, carbon has 6 electrons. The first 2 electrons are going to go to the 1s orbital. The second 2 to the 2s orbital. And because carbon has 3p orbitals and only 2 electrons remaining, the first 2p orbitals will both receive 1 electron. If you look at nitrogen, the same applies. Now nitrogen has 7 electrons. The first 2 will go to the first s orbital. The second will go to the second s orbital. And because nitrogen has 3p orbitals and 3 electrons remaining, each one of the p orbitals will first get 1 electron before any pairing can occur. You have to bear in mind this rule applies to each orbital receiving 1 electron before pairing can occur. So if you look at carbon, I could have easily paired those 2 electrons into one of the p orbitals, but that would be against Hund's rule. Hund's rule states that each one of those orbitals in that same energy sublevel, so the energy sublevel we're talking about now is 2p, each one of those electrons must be placed in an individual p orbital before any pairing can occur. The second part of Hund's rule stated that each orbital must receive 1 electron with the same spin as the next orbital. Again, this occurs before pairing happens. And so look at nitrogen. Nitrogen, each one of those 3 electrons in each of the p orbitals are all facing up. They're all spinning with a positive spin. And so you must fill each one of those orbitals with a positive spin before you can pair with a negative spin. I'm concluding this lecture with a quantum numbers example. It is my hope that this example clarifies any confusions you may still have, and that it ties all the quantum numbers together in a way that you understand. I'm choosing a lengthy example here so you can use it as reference when studying for a quiz, a test, or answering questions. The example I'm choosing is the selenium ion. Now, based on its position on the periodic table, it has 34 electrons. That means that you have to write out 34 separate lines for each electron, each line with the 4 quantum numbers for each electron. But in fact, because I've picked the ion here, we're not actually doing 34 electrons. We're doing 36. What we're actually doing is writing out the quantum numbers that are equivalent to krypton. Before we begin, I would like to draw your attention to the atomic number of each element. At the end of every line that I complete, I'll be writing the symbol of an element. This is because at the end of the first line of quantum numbers, I would have written those equivalent to hydrogen. At the end of the second line, those equivalent to helium. At the end of the 24th line, those equivalent to chromium, and so on and so forth. This example is a great reference because it clearly outlines the quantum numbers of every element leading up to krypton. At the start of any example, it is important to remember that the orbitals in the lowest energy level must receive electrons first and become filled before you can move on to the orbitals in the highest energy level. It begs to reason that we would start with energy level 1 because the s orbital in that energy level is closest to the nucleus. So we start by writing n equals 1. Now if n equals 1, L must equal 0. And that's because of the limits that n equals 1 places on L. If L is equal to 0, then ML must also be equal to 0. So what I'm going to do now is I'm going to place an electron into this s orbital by writing ms positive 1/2. So that's the positive spin electron. What I've written now are the quantum numbers equivalent to that of hydrogen. I'm going to place a second electron in this s orbital by writing ml equals 0 and ms equals negative 1/2, the negative spin electron. Now I have quantum numbers equivalent to those of helium. I've now filled the first orbital, and really the only orbital in the first energy level. Now I can move on to the second energy level. Before I do, you'll notice that I didn't write n equals 1 and L equals 0 for the second line, because it's redundant. As long as I write the ML and MS of every single line, I've essentially accomplished what I need to accomplish. The only time I need to write the first two quantum numbers is when I'm moving on to a new energy level, okay? Or I'm moving on to a new orbital type. So now I'm going to move on to the second energy level, n equals 2. The second energy level has two types of orbitals. It has an s orbital and it has three p orbitals. Now before I fill the p orbitals, I need to fill the s orbital. And this is denoted by the value of L. So if L is equal to 0 for S and L is equal to 1 for P, it only makes sense to start with the lower value first, to fill that lower value, hence why they gave it a lower number. And so I'm going to write L equals 0 and start with the S orbital for the second energy level. Its ML will again be 0, and I'll place a positive 1/2 electron. Now I have the quantum numbers for lithium. The second electron will now be a negative 1/2, and this is beryllium. Now I've filled the s orbital in the second energy level, and I'm now going to move on to the p orbitals. I do this by writing L equals 1. Now you have to remember that for L equals 1, ML ranges from negative 1 to positive 1. And so I start with the lower integer, negative 1. And so ML will be negative 1. I'm going to put my first electron in that orbital. Now I have boron. And many would think, okay, well now I'm going to fill the negative 1 orbital with a negative 1/2 spin electron. So you're thinking, let's just fill that orbital. In fact, that's not what we're supposed to do, and the reason being is because of Hund's rule. Remember, Hund said that we need to fill each one of the p orbitals with 1 electron first before we move on to the second electron, before we pair it with the opposite spin. What's more is each electron that we place into a p orbital must have the same spin. And so what I should be doing now is ML equals 0. So that's the second p orbital. And I'm going to place, again, a positive 1/2 spin electron. Okay? Now I have carbon. I'm going to place the next electron into the ML positive 1. Okay? This is the third p orbital. And it is another 1/2 spin electron. I have nitrogen now. Now that I've filled each one of the p orbitals with 1 electron, I'm now going to pair each single p orbital with an opposite spin electron. And so I'm going to start again now with the negative 1 ML. And add, as you can see here, a negative 1/2 electron. Now I have oxygen. Keep in mind, what I have written here, this whole series, would be the quantum numbers that I would need to write to get to oxygen. So if I just asked you a question, what are the quantum numbers for oxygen, it would be what you see before you write now. Okay, you'd have to write the whole series. You can't just write that one line for oxygen. So when you see these elements symbolized on the right here, you can't just write that one line. You need to write all of these quantum numbers to arrive at that one element. And I'm now going to continue with ML equals 0 and MS negative 1/2. I now have fluorine and the last p orbital, and I have neon. At this point, we've concluded with the second energy level. Now we need to move on to the third energy level. So n equals 3. Remember, we're done with the second energy level because we've filled the s orbital and we've filled the p orbitals. Okay, what you can see here is I've half filled the first 3 and I've paired them again with their negative spin. The third energy level is a little bit different from the second one in the sense that it has three types of orbitals. It has the s orbital, it has the 3p orbitals, and it has 5d orbitals. Okay? And so it gets a little tricky when we're doing the third energy level, but we're going to start the exact same way, just like we started with the second energy level. We're going to start with the s orbital. And so I'm going to write L equals 0, ml equals 0. I'm going to put the first electron in. I have sodium now. The second electron, I have magnesium. Now that I've filled the s orbital, I'm going to go on to the p orbitals. So -1/2, its electron. Remember, it's going to be all positive spin for the first three. So I have aluminum, positive spin. I have silicon, positive spin. I have phosphorus. I've now half filled the p orbitals for L equals 1. Now I'm going to pair it with the opposite spin. Okay, so sulfur, chlorine, and argon. So now at this point, I've filled all of the p orbitals for the third energy level. Okay, now at this point, it would only make sense to move on to the d orbitals that are now in the third energy level. But in fact, if you look at the periodic table, the d orbitals don't come first. It's the s orbitals for the fourth energy level that come before the d orbitals of the third energy level. Let me show you what this looks like on the periodic table. This image here shows the relationship between the periodic table and the orbital sublevels. As you can see, in group 1 and 2, you'll have the s orbitals, with one exception, helium, located over here in group 18. And you have all of the p orbitals located between group 13 and 18. The d orbitals are the transition metals between group 3 and 12. And interestingly enough, you have the f orbitals sandwiched in between the d block and the s block. And again, that's what we call it. We call this the d block, and we call this the s block. We call this the p block. And this, of course, would be the f block. And so we have the f block sandwiched in between the d block and the s block in periods 6 and 7. Now, I'm going to explain a little bit more about the f orbitals in the next lecture. But for now, we just finished filling the orbitals up to argon, which is this element right there. And so we need to now fill the d orbitals. But before we can fill the d orbitals, these d orbitals here, to get to krypton, which is located right here, we actually need to fill these two s orbitals. Elements 19 and 20, potassium and calcium. And the reason being, if you look again, we finished filling argon at the end of the 3p block. But before we can get to the d block, we need to fill this s orbital in the fourth energy level. And so that's why we actually have to jump from the 3p to the 4s before we can get to the 3d. So going back to our example, we've just written all of the quantum numbers for the elements leading up to argon. And we just finished filling the p orbitals in the third energy level. But as I just showed you, we need to go from the third p orbitals to the s orbital in the fourth energy level before we can get to the d orbitals in the third energy level. And so to do that, we need to write n equals 4. And of course, we denote the s orbital in the fourth energy level by writing L equals 0. Ml is of course equal to 0. And you have the first spin electron, the positive spin electron. That will be potassium. The second spin electron will be calcium. Now that we've filled the s orbital in the fourth energy level, we can now jump to the d orbitals for the third energy level. We've now arrived at the 3d orbitals. And as always, we're going to start by writing the energy level, n equals 3. In this situation, L will be equal to 2. We don't have to worry about L equals 0 or L equals 1 anymore, because we've already filled those orbitals. So we can jump directly to L equals 2. As always, ML ranges from negative L to positive L. And so in this situation, our ML will be negative 2. I'm going to place an electron in this orbital with a positive spin, and that gives me the quantum numbers for scandium. Now, please bear in mind that Hund's rule applies to d orbitals just as it applies to any other orbitals. So as you saw with the p orbitals in the last slide, we need to fill each one of the d orbitals with positive spin electrons. We must half fill those orbitals first with positive spin electrons before we can then go back and double up with an opposite spin electron. And so instead of writing another line for negative 2, I'm going to write the next line as negative 1. So I'm jumping directly to the next d orbital. Again, I'm going to give it a positive spin electron, as all the half-filled orbitals must be filled first with a positive spin electron. That gives me titanium. The next orbital will be 0, positive spin electron, vanadium. And now I'm going into positive 1, positive spin, chromium, positive 2. So this is the end of my range for the d orbitals. Positive spin, and manganese. So now that I've filled my d orbitals with a positive electron, I'm now going to double up those d orbitals with a negative spin electron. So I'm going back now to negative 2. I'm going to place a negative spin electron, and I get iron. Negative 1, cobalt. 0, nickel, and positive 1, copper, and positive 2, zinc. And so by doing what I've just done, I've half filled the d orbitals first with positive spin, and now I've filled the d orbitals by pairing up those half-filled electrons with a negative spin. And so now I've completed my d orbitals for the third energy level. And so before I move on, you need to now bear in mind we've jumped now from the 3d to the 4p. If we go back to the periodic table, I can show you what that looks like. So we've just finished writing the quantum numbers for the elements in this highlighted area here. The last element we wrote a line of quantum numbers for is zinc, right there. Now you can see, after the d orbitals, we now move into the 4p orbitals. And so we now have to jump again. We jump from the third energy level back to the fourth energy level. And so we've done this now twice. We've jumped from the 3p to the 4s, and then from the 4s to the 3d, and now we're going to jump back to the 4p. Here we have the completed d orbitals for the third energy level. Now I'm going to jump back to the fourth energy level to complete the p orbitals. So to do this, I of course have to write the energy level, n equals 4. Now I've already completed the s orbital for the fourth energy level, L equals 0, and so now I can jump directly to L equals 1 for the p orbitals, so L equals 1. Remember that ML ranges from negative L to positive L, and so I'm going to start with negative 1. I'm going to half fill this orbital with a positive spin electron, and I have gallium. Now, as always, I'm going to half fill each one of the p orbitals first with a positive spin. So I'm going to go to the next orbital, which is 0, positive spin, germanium. And then the next orbital will be positive 1, positive spin, arsenic. And now that I've half filled my 3p orbitals, I'm now going to fill them by pairing them with a negative spin electron. So going to my negative 1 again, negative spin electron, I'm now at selenium. Now, some of you are thinking, oh, we're done. We're at selenium. Well, actually, I've picked out the selenium ion as my example. And so you can see that the selenium ion is 2 negative, meaning what I've done is I've added 2 more electrons to selenium. So if you follow that to conclusion, in fact, I'm not stopping at selenium. I'm stopping at the quantum numbers that are equivalent to krypton. And so the next electron I need to add will give me bromine. And finally, I'm now filling my 4 p orbitals with the last negative spin electron, and that gives me krypton. And this would be the completed set of quantum numbers for the question of the selenium ion. So I hope this example has clarified things for you. I hope it shows you how these quantum numbers work in relation to each other. And I also hope that you can use it as reference for future questions and homework that you may use as practice. This slide and the next slide are essentially review slides. They provide charts that organize all of the information that we've discussed in this package. They show you all of the sublevels and all of their respective quantum numbers to the maximum values that you can have for each quantum number. This table is a little bit more streamlined. Essentially, it shows the maximum number of electrons you can have in each sublevel, or the maximum number of electrons you can have in any one energy level. Okay guys, so I hope you enjoyed this package. I hope you understood this lecture. It was a pleasure. All the best.